Hey everyone, we're back with week 3, chapter 4. We're going to get into more of a better definition of the atom and what you're going to expect to see outside of the nucleus in particular. A couple of things we're going to see throughout several videos in this chapter will be radiation, how you can compare one type of light to another, one type of radiation to another. Then we're going to see the history lesson of how we've organized outside of that nucleus, outside of that marble in our Bush Stadium kind of model. And then we're going to eventually see how we can excite electrons from their ground states and what that really means with respect to our stadium. We'll also see electron configuration and valence electrons and how we can see that from the periodic table specifically. And then lastly, we're going to revisit some size and ionization trends with respect to electron configuration and show how we can use the octet rule for our main 8 groups to apply these electron configurations and their charges for their anions and cations and how they can get together to make compounds. So it's a big chapter. It's probably one of the biggest chapters of the early part of the semester, and it all starts with light. Light is the easiest way for us to understand what electrons are doing because electrons are required for most light bulbs to produce light. So what does that really mean? Well, if you're looking at this slide here, you're seeing that hydrogen has this kind of pink-purple color. And the only reason that we can see that pink-purple color is because our eyes are mixing together the blue, the green, the yellow, and the red lines that are visible from us through a prism as kind of a mixture. So it'd be like taking 4 colors on a palette from art class and then mixing together, and that's what our eyes are seeing. So in lab we'll be able to look at different elements through a prism and see that they have different line spectrums, so they're each specific. Those are actually called atomic fingerprints. And because each atom has different number of electrons in their stadium, they can produce different spectra of light. So that's an easy way for places like NASA to look at other planets, to look at other galaxies, and see what kind of elements may exist in some of those planets based on some of the colors that they're seeing back here at Earth. To understand light, we first have to understand what it's doing, what it looks like behind the scenes. Light is a particle in the sense that it's very small and it moves in a wave. So it does this at the same time. So it's a particle moving in a wave simultaneously, and this is called a photon. Be careful not to confuse that with a proton, which is very similar in spelling, but very different in concept. Photons are just an energy in a particle-like feature. You can imagine if you were to have static under a blanket and you see those little sparks of light, that's exactly what a photon is. For us to be able to view a light bulb, it takes billions, trillions upon trillions of photons per second to produce something visible and bright enough to light a room. So if light behaves both as a particle and a wave, how can we distinguish one from another? Can we distinguish which one's more dangerous, or which one has a higher frequency or a longer wavelength? Those are the kinds of things we need to understand to better understand light in general. So that's what we're going to be after for quite a while. And so we're going to talk about that first. Oftentimes you can think of life experiences to help you understand the difference. Our body is capable of seeing a very small range of light. This is what we call visible light. The longest wavelength we're able to see is what we call red light. And the shortest wavelength of light that we're able to see is violet. You can imagine that if we were to look at these waves and their wavelengths, notice the wavelength is really just the distance here from kind of peak to peak. So obviously this one is a little bit narrower from peak to peak, so that's where we get that differentiation of wavelength. That's the distance between mountain to mountain or valley to valley. However, if we were to think about frequency would be about how many waves per second. So what that really means is if we were to take a slice of this and say, what if this is 1 second of time? That would tell us that there's more waves in, say, violet light than there would be in red light. More waves per second means more danger. So this is what we see as an opposite in chemistry. Wavelength and energy very directly related to frequency. Those are opposites. As things get longer in their waves, they're going to get a lot softer when they hit, say, tissue in your body. So just be aware that wavelength and frequency is the waves per second, so to speak. That's going to be a way to tie back to energy in particular. And energy is always going to be opposite of wavelength. As we're to look at the color of lights that we can see, this can be reminded through what you learn in art class. So if you think of the colors of the rainbow, you can do Roy G. Biv backwards. So Roy G. Biv backwards will help us understand the portion of light that we can see. So again, red is the longer wavelength, so wavelength would go this way, as you can see from the slide itself. But as you go in the opposite direction, that would be energy and frequency. So the frequency gets higher along with the energy. And this is all related to danger. So danger to our bodies. So red would be the safest color of clothing to wear, so to speak, if it were theoretically that much different. In the grand scheme of things, the difference between red and violet isn't enough to be harmful to us. But theoretically, or at least mathematically speaking, violet is a higher energy than red based on its wavelength. So as we look at the electromagnetic spectrum, how can we think about this in terms that we can remember rather than just a random chart in which to photographically memorize for the exam? So let's take a minute to think about this again on our own. So what we're going to do first is try putting Roy G. Biv backwards. Again, this is the order of danger from right moving to left. This is the visible region that we can see. And outside of that, we can take some clues to know who's next. For example, we can say that next to red is infrared. Infrared is heat. This is like campfire. This is actually the easiest wave to see because you can look down a highway in the middle of the summer or on the hood of your car when it's getting heated up by the sun, and you'll see those heat waves come up. So it's the best representation that radiation moves in a waveform that we can actually see. It looks clear, but you can see it in that wave kind of curly format. Go to the opposite edge of the visible spectrum and you're going to see V for violet. So that's purple. And that's next to ultraviolet, which for us we have to worry about with the sun because those ultraviolet rays can damage our skin if we don't wear sunscreen. So those sunburns tells us that that is the direction of danger, which helps us understand this without using our textbook. So as we move in that direction, this would be the direction of danger. But that's also the direction of high energy. That's also the direction of high frequency. In the opposite direction, because energy and frequency are related over on this side, you're going to see those waves go very fast. And then as they start to get on this other side, they start to get longer and longer and longer. And that's because in the opposite direction is wavelength. Wavelength and energy being opposites. So as we expand out from danger and from things that are less dangerous, let's do dangerous first because it's a little bit easier to think about. If you're looking at UV rays, you're thinking of sunscreen to protect you. Something that's even more dangerous yet would say be X-rays. X-rays, you need a lead vest in order to protect you there. Even more dangerous than an X-ray would be a nuclear weapon, and that would be, say, a gamma ray. Even more dangerous, and we'll talk about gamma rays in more detail and how they're produced in our week 4 chapter next week. The most dangerous of all is in outer space, and those are cosmic rays. but unless you plan on traveling to the sun, you don't have to worry about those too much. As we go on the less dangerous side over here with IR, this is the same kind of light that's used in, say, trail cameras or checking your insulation in your house to see if it's has a high enough rating. You see a lot of those infrared kinds of ideas in war movies and so forth, where you're seeing those heat signatures of people. Less dangerous than IR. This one's probably the most misplaced out of all of them, and this is microwaves. And that's because microwaves, when you put in some popcorn, doesn't turn out well for those little kernels. The reason that we call these microwaves is because they're measured in micrometers. Everything over in this region is kind of in that nanometer, even maybe picometer range eventually. But that's just a use of the metric system where we're looking at millions versus billions versus trillions of a meter and so forth. But microwaves aren't dangerous. If you look at your microwave while it's on, it's not going to hurt you. That machine is designed to focus all that radiation right in the center of where that food item happens to be. So it's just the way that we use that radiation that it appears dangerous. And then this last one is the one that your parents don't want you to know about. This is your TV, your radio, and your cell phone waves. These are the longest of the bunch. These are the safest of the bunch. So when your parents tell you that your TV is going to give you eye cancer, or your radio is going to give you ear cancer, or your cell phone is going to give you brain cancer, it's to tell you to take some time away from those items. Not scientifically speaking, the radiation that they're producing is not dangerous. It's actually the longest wavelength and the least energy of all of them. But hopefully by walking through this idea, you see that just using your life experiences and understanding sunscreen versus lead vests when you go to the dentist, versus heat or microwaves, now we can better put those into a useful concept so we can better think about it when it comes test time. So again, as we look at the electromagnetic spectrum, we want to make sure that you understand this idea of who's higher energy, who's lower energy, and what that really means when we compare one to the other in homework questions and exam questions. We also have a way mathematically to understand radiation. In this equation, you can see that energy and wavelength are opposites, and that's what we said earlier. So h, Planck's constant, c, the speed of light, those are constants, and that number doesn't change on top in the numerator. But what does change is the wavelength you plug in underneath it. So by plugging in a various wavelength, you can see that as the wavelength gets bigger, you'll be dividing by a larger number, and then energy will go down as a result. So the take-home message here is that high energy is going to have a short wavelength, because then you're dividing by a short value in that calculation. Low energy would be a long wavelength, because then again you're dividing by a large number, getting out a short answer, or in this case energy in the end. So what does all this light mean? Well, because elements show specific discrete lines of light, that means that we have to worry about what it means to have all this empty space. So what does that empty space mean? What do these dark regions represent? Why is it not just a bright rainbow like you see in the sky? Those are things we have to cover in our next video coming up, and this will give us an idea of how physics changed forever. So we'll see you then.